Press pause and see how quickly you can write all of these down. Check each other. Then we'll see if you beat my time. All right, here we go. 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, 144, 169, 196, 225, 256, 289, 324, 361, and 400. Cubes are where we are multiplying 3 roots and not just 2. So when you think about it, it's just the volume of a cube where each part of the cube is the same length. Now 1 is the most interesting number because it's its own square, it's its own square root, it's its own cube, it's its own cube root. But when you switch and change to 2 on each one, 2 times 2 is 4, times 2 is 8. Now, I expect you to have these 5 memorized, where you can recognize them on sight. So 3 times 3 is 9, 9 times 3 is 27. 4 cubed is 4 times 4 times 4, which is 64. But if we went back to 2 cubed is 8, and then squared the 8, we'd still get 64. If you went back to 2 squared and cubed, you get back to 4 to the third. Exponents are real tricky like that. 5 cubed, 5 times 5 is 25, times 5 again is 125. I will see this one often in standardized testing. 6 cubed is 216, 7 cubed is 343, 8 cubed is 512, 9 cubed is 729, and 10 cubed is 1,000. You will see these numbers referenced in many different tests where their allocation of time to complete the problem is not based on how long it takes you to figure out. Now, you caught a little bit of this doing this when I was teaching this in class yesterday, but knowing these fraction to decimal equivalents by heart, again, is a huge calculation leverage. When you get a whole new set, recognizing numbers that you already know, like 2/4 being 1/2, it's important that you can take what you know in a different context. Now, a lot of people say this as 1/4, but if you say it as a quarter, that helps trigger your brain because you know that 1/4 is 25 cents. 3/4 is 75 cents. And obviously 4/4 is a whole. I want you to use a calculator and see if you can figure out the patterns with these. Let's see if you were able to do it. Press pause, give yourself time to work on this, and go forward. All right. 1/3 is probably one of the first ones that you've ever dealt with, as being 0.333 repeating. How do you know that? You tip the chair, turn the fraction on its side, and you go into long division. Just like most of us, we do not like long division. But the first thing you do with long division in a decimal is you take your decimal and you transplant it to the top. Then you see how many groups of 3 you can pull out of 10. 3, 6, 9, 3 groups. You subtract the 9 that you're pulling out, because that's how many are in 3 groups. And you're back with a 1. Add a 0, bring down a 0. Oh, wait, we're just going to keep ending up with that. That's how we get 0.333 repeating. Now with 2/3, that's doubled. You can do the long division if you want, but if you can recognize the doubling, 3 doubled is 6. Sometimes you see it as 0.67 because, of course, this 6 would bump the 6 in front of it to a 7. And 3/3 is a whole. Now, if you're thinking the 6 is like, I don't want to do all the division, you really don't have to. There's something special with these 3, that you already know these decimal equivalents before you even do any long division. Press pause and see if you guys can figure that out. Did you guys figure out that 2/6 reduces to 1/3? And we already know 1/3 to be 0.33 repeating. Going over here, 2/4 reduces to 2/3, and oh yeah, we already know that. 0.666 repeating. 3/6 can be reduced. That's the same as 1/2, like we did for 2/4. And we know that's 0.5. So really, there's only 2 new fractions to learn when it comes to 1/6 and 5/6. 1/6 is the only time the misconception that so many people use works. It's when that if you take the denominator, tip it, and divide 6 into 10, you add a decimal, add a 0, but then this decimal is going to get transplanted up to quotient. 6 goes into 10. You can plot one group of 6, subtract the 6, and then you get 4. So it's not going to be repeating with the 1. But if you add a 0 and bring down a 0, 6 times 5 is 30. 6 times 6 is 36. 6 times 7 is 42. That's too far. So I can pull out 6 groups and subtract the 36. (40 minus 36, 39, 38, 37, 36). It's 4, and there's our pattern. Add a 0, bring down a 0. So the 6 keeps repeating. So this is the only time that the numerator is the first number and the denominator is the second number. Now, 5/6 is 0.16 less than a whole. So it's this in-between number. So if you took 1 minus 0.166 repeating, all of a sudden we've got the borrowing problem that never ends. Since I can't subtract 0 and 1, I'm going to bring over the 1, and 10 minus 1, but I can't do that yet. I've got to borrow here and make that a 9, and then borrow here and make that a 9, and then borrow here. So 10 minus 6 is 4. 9 minus 6 is 3. 9 minus 1 is 8. And somewhere this usually ends up to be another 3. Just 0.888333 repeating. I'm making a subtraction error somewhere. But really, all you had to learn, oops, not that one. All you had to learn was that 1/6 is the same as 0.16. And 5/6 is the same as 0.833. Right, see if you guys can figure out the pattern for 1/5, 2/5, 3/5, 4/5, 5/5. I'll give you a small hint. Find the equivalents if these were all fractions over 10. Then the decimal should fall right out at you. All right, 1/5 is the same as 2/10, which is 0.2. 2/5 is the same as 4/10, which is 0.4. See the pattern? 0.6, 0.8, and 1 whole. Now, using your long division, find the pattern here. So if we go over here to our lovely friend Desmos, and we take 1 divided by 9, our pattern is 0.111111. Now that you see this, you don't have to go divide the rest of them, do you? Maybe to see the pattern one more time. 2 divided by 9. Oh, looky. It is 0.22222222 repeating. And the same holds true for everyone. And you want to say 0.9999 for 9 nines, but that is just one whole. Now, what if the pattern takes up 2 decimal places? When it was 0.222 repeating, it was 2 over 9. But now it's the 24 that is repeating, and the decimal is 99. Kind of exciting. But you won't ever see that one as an answer. And the reason why is because that dude can be reduced. So think of factor pairs. I know 24 is 8 times 3, and I chose 3 because 2 doesn't work with 99. But if I think about 3 times what is 99? 3 times 33. Matching factors cancel, and it's 8 over 33. That's the fraction you will see. That's the pattern that you use. All right. I've given you a hint. Pause it and see if you find the right answer. Did you remember to change 16.6 to a decimal? And that told you that this was the answer? What if, for whatever reason, you forgot that relationship? You could go back and eliminate the others in case you're worried and find the decimal equivalents and realize that number one is the only one that works. Okay? Work with your partners to finish this one. All right. Looking up here at these fractions, I know these relationships. I know that as a fraction, this is 1 2/3. And I do know that that is 1.666 repeating, which is right here. These ones were super easy once I figured out the pattern. That's this guy right here. But it's hoping that you remember that these symbols mean repeating. Now, this number is less than 1, and this is the only fraction that's left that's less than 1. So that has to be it. And the reason why I know this is bigger than 1 is because it's 32 ninths. If you break 32 ninths up, you get 9 ninths, another 9 ninths, another 9 ninths. So that means it's 3. And that means I've got 5 ninths later, which we know is 0.5 repeating. So this one has to be 32 ninths. Most of the time when you have a multiple answer problem like this, it is really important that you take your time, do the ones you know for sure, and then work your way to the other ones. You already did that one. This one's a challenge. I want to see what you guys can find on the internet for that one. This one should have been easy peasy. Did you get 7 ninths? All right. Referring back to the perfect squares that we did at the beginning of this lesson. When you have a variable that is y squared, your answer is going to have 2 solutions. Your exponent tells you how many solutions you're going to have. This, along with everything else over the next 4 years, is one more inverse operation that you're learning. You spent all of 7th grade learning about multiplicative inverses. We learned about additive inverses. And we learned them as steps to solve equations, to remove obstacles that kept you from your variable. The most basic one we learned first, which of course you do in your head now, but the additive inverse of adding 2 is subtracting 2. Whatever you do to one side, you do to the other. These cancel, and then it equals 3. But the whole point of this process here is to highlight how you learned to do inverse operations to get your variable by itself. Well, this time our inverse operation is an exponent of 2. And whatever you do to one side, you've got to do to the other. Now, for some reason, the literature made it a z instead of a y. Knowing what we know about 169, the square root of 169 is 13. But there's a plus and minus in there. Now, if we go to Desmos, graphing calculator, let's just go ahead and make it x for Desmos fun. X squared equals 169. And if we zoom out, this point right here is negative 13. And this point right here is positive 13. Why is there a positive and negative? Well, in the world of math, squared means times by itself to get an answer. And sure enough, 13 times 13 equals 169. So that checks. But there is another solution of negative 13 times negative 13. A negative times a negative is a positive. And we still get 169. Now, you are beginning to learn in this process, mathematicians are lazy as can be, and we like shortcutting how we write something. But your two solutions are negative 13 and positive 13, because in that graph, it crosses here and here. This is the graph for the equation we just solved. Everything we're solving this year is going to have solutions where they are crossing the x-axis. That is what a solution is. Now this time, the inverse that we're learning is the squared. I mean, cubed root. This is b cubed equals 1,000. Well, back on our sheet of sheets to remember everything, 10 cubed equals 1,000. This time, the inverse operation is the cubed root. Now this time, there's only one solution. Because to have a positive 1,000, you can only have positive tens. If your roots are negative tens, a negative 10 times a negative 10 is a positive 100, times a negative 10 gets us to a negative 1,000. And that is not the root that it gave us. Now this one's an interesting graph. When you go to Desmos, we end up making everything x. And it just goes on forever. But did you see where it crossed? Only once, and it crossed at 10. There's only one root, and this graph crosses at 10. So Desmos is a really handy tool for you to check the solutions that you get to see if that works. I want you to take what you've learned and I want you to solve these problems. Work with each other and let me know when you guys are done. And I will have this there for you. Got lots of problems here to solve. Don't worry about the end. Those are last year's back in the day seating charts. But there you go. You guys got this.